ones, right? So sometimes the transverse ones can be degenerate, so that means you get one longitudinal acoustic and maybe one transverse acoustic. So typically you expect 3 depending on the crystallographic direction, right? Going from that gamma point to X point and things like that in the building. So this is the case. So please remember there are no modes for high frequency. These are all low frequency at k equals 0, right? But when you have this diatomic for a given unit cell, if you have 2 atoms, one has mass m1, other one has m2, then situation is completely different. So you will start seeing some branches, they have high frequencies. So I will explain why this acoustic and optical modes. So if you have some light coming, suppose some photons, right? If they interact with these phonons, phonons are basically your vibration in the crystal, right? Those light can interact with the phonons. So then that light, it comes with certain wavelength, so then outgoing wavelength will be different because it interacts with these phonons, right? So this kind of scattering we call Brillouin scattering. So next, if you have this kind of thing, this optical, right? So these phonons, actually they are high energetic photons, the phonons. When they interact with light, that's what we get the Raman scattering. So this gives you. So okay, now let's look at how this one works. So again, we'll use that same model, right, for the spring constant. So if you have a certain position, you can just actually if you let me. So this one. So I will show you how to prove this one. So in the single monoatomic case, if you remember, your omega was simply 2c over m sine k over 2. Very simple, right? The sine relationship. Basically, you have this is sine curve, right? So this is what we had for the monoatomic case, right? Sine. So this is pi over a minus pi over a. This is sine curve, right? Basically. But here you will see this is much more complicated, right? So how do you get this one? Again, you can see whenever you have omega goes to 0, when k goes to 0, that is this situation, okay? That they are called the acoustic modes. So when k goes to 0, if omega has some, not 0, it's some higher value, they are called the optical modes. So let's try to derive this expression. Very simple actually. It's basically what you do is, this is your equilibrium position. Only thing is these masses are different, right? Now. So suppose this has initially at this position. Now if they start vibrating, so they will move to different positions, right? So each one is, say, the nth particle of m that moves by distance, say, un, but the m particle, so that moves with different distance, right? That means that you will have 2 equations. So you have to write the Newton's second law, that's basically m d squared u over t squared, right? This you have to write for m1, and also you have to write for d squared, say v over dt squared for the second particle. Then you have 2 coupled equations, right? So then you know how to solve for that one. That's still pretty straightforward. So initially I thought maybe it's here. Let me actually, this is easy to. Let's look at this one. Let's write the equation. Let's say this one has mass m1 M2, you can see the large one, smaller one, right? Large one, smaller one. Suppose this is mass capital M1. So if you write suppose this one is moving by, displacement is say US. So then this one moves by, we'll use the two notations. So M1 particle, your displacement I will write as US plus 1, US minus 1 like that. So the M2 particle, they are moving by, say, S particle is moving by Vs, right? This one is moving by V, S plus 1, this is moving by S minus 1. So then you can easily write the equation for, say, this is the M particle moving by, say, US, right? So then what is the equation? M1 d squared US over dt squared equals, you can write if your constant is C, you can write 1 to the right, so this is M1, so then if I go this way, right? So you have M1, I can show it from here, right? So this is M1, so then what you need is, because the spring attached, I think displaced by this one and this one, then you have to take the difference, right? That you can write as your first one, since this is US, this is to the right, it is VS, right? Then VS minus US, right? VS minus US, then plus C, then what you have here is, this is, if I write this one as S1, this is S plus 1, okay? This is S minus 1, the particle position. So then this is, if you write that one, you get, you can easily write this one here. I have, if you write this way, you get Vs minus Us. Then you have plus, from this side we have Vs minus 1, right? Minus Us. Yes. So if you take sum, then you can see what you get here. So you get C, you have Us twice, right? Us, if this is negative. You can do this one. If you do this one, you get Vs plus Vs minus 1 minus 2 Us. So same thing you can write for the second particle, M2, then d squared Vs over d squared, right? Then you can do the same thing. So you do that one, you get this equation. Exactly. So very simple, right? So because each spring, because you have to think, this is moving by US, this is moving by V S plus 1, right? So that means you need to get the difference between the two. So this is what you can easily write two equations. Now you have these two equations with two parameters, right? U's and V's. So then how do you solve this one? You have to write the solutions for each US and VS. So previously we had only, say, U's, right? It's only M particle. So then it was easy, but in this case, then you can write your US as some exponential, say U times E I K SA, right? Kx means SA minus omega T. Right? Vs you can write as V times EI, you say your X, S means A times S, right? Is that clear? So EIKX. X means the particle position and the S position, right? That's A times S. That's why this one you can write as KSA minus omega T. Right? So now just plug in these numbers. what is d squared u over dt squared? Here, if you take the second derivative, you can see minus I omega comes out, right? So you have to do twice, then minus I omega squared. That's why you get, oh yeah, here is the solution. So here US is this one, VS is, and this is basically SK. Here they have capital K or something. Now, again, so you have to take the second derivative, you get omega squared, that's fine, right? So then if you plug in Vs, you put this one, then here Vs minus 1 means this becomes S minus 1, right? Because X, this is X. S plus 1 means A times S plus 1. X. S minus 1 means A times S minus 1, right? So if you put that one, you get, write down the equation, then you will see all the omega t terms cancel out. So then also S term cancels everything. So but if you have this here, you get plus A, here you get minus A, right? So if you do that one, this is the equation you get. Very simple, right? You can easily just substitute these two equations here and just cancel out omega and ISA. You can see two equations, right? Two coupled equations. How do you solve this one? It's only you have to solve for uv, right? So then if you take u, you have something like u times something plus v times something equals 0, right? So then you have second equation also, u and v equals 0. So then you can solve for u and v. So basically if you do that one, what you have to do is just basically take the determinant of this one, right? So then that equals 0 means you get the solution. So if you want to solve for uv, then you can go back and show what is the u and v. Yes. So if you do this one, that's the determinant. So this time you can see where you get this term here. This one has 2c u. If you take u, I have 2c minus m1 omega, right? This one. U, v has c times 1 plus this one. Again, v has 2c minus m. That's the determinant, right? Is that clear? So that equals 0 now. If you want to solve this one, you multiply this one, you can see omega squared, you get omega 4, right? So then your equation becomes this, that's the equation. This omega 4, omega squared, this one equals 0. So this is actually quadratic equation of omega squared, right? So that's basically, you know how to ax squared plus bx plus c equals 0. So basically then your x is basically the square root of that minus b plus or minus, you know, so that one you get plus or minus b squared minus 4ac divided by 2a, right? If you do that one, you get solution for what? Omega squared, right? The omega squared is the your quadratic equation. If you solve that one, this is what you get, omega squared, you get two equations. That's kind of very long expressions, but we make the this equal. So if you, because you have positive and negative, right? So we'll make the two, because this is a really long equation. Actually it's not bad. So, but we will make the approximation for this Ka goes to 0. So that means that this smaller wavelength region, right? So if you do that one, you get two solutions. Why you get two solutions? Plus and minus thing, right? So you have here plus or minus. You get one solution. This is 2c times this one. other solution is this one. So that is for, if you look at this one, what you get is solution is something like this is, you get 1 for, this is say K or KA, doesn't matter. This is omega. For Ka goes to 0, that means somewhere here, right? You get one solution that goes like, this is omega squared. That means omega is K times A, right? So that means it goes like this one, right? But it still, that's the low limit. That's the acoustic mode, right? So other one is what? When K, that's a constant term. That means that has value here. So that has the value of square root of, that's omega square, that means square root of 2c 1 over m1 plus 1 over m2. So that is this one. Exactly. That is for Ka goes to 0. So this is one, we call this is acoustic mode. Acoustic means when K goes to 0, omega goes to 0. In the other case, when K goes to 0, omega goes to some omega maximum value, right? That is given by this value. Is it okay? Okay, so now if you take the other limit, what is the other limit? K goes to pi, right? Because if you remember your brilliance zone, when K equals pi over A and minus pi over A, so this means Ka equals actually pi. So if you do that one, you get, yeah, so that is basically this value. This one we know. But if you calculate for when Ka goes to pi, just these are the two numbers you get. One is 2CO M2, other one is 2CO M1. So we'll say M1 is larger than M2. There are two masses, right? If M1 is larger, that means this number is smaller, right? Right? That means you have, this is at here, we know here this is 1 and this is 1, right? At pi value, you have 1 that is 2C over M2. If M1 is larger, so then this should be square root of, no, that is square, then square root of that one, right? So that means you have, what is this omega is 2C over M1, that's smaller number, right? So actually, half of that one, right? So other value is square root of 2C over M2, right? If M2 smaller means this number is larger, right? So that's what it is here. So that means the value becomes like this. Initially we know it is like this, then it is going like this, right? Get into this. Actually, in this case, actually they have considered M1 to be smaller than M2. That's why this number is no, that's correct. Yeah, I think it's M1, right? That's fine. So in the other case, we know this is 1, so other value is larger value. So that means this one has some kind of, we don't know exactly how this one, but we know the two values. So typically, so this has very little dispersion, but this one has a very large dispersion. But at either point, at this point, always this one is, actually if you look at this one, it's going something like this. This should be 90 degrees. So is that clear how the, so this is the optical mode, this is the acoustic mode. So but ideally you have 3 modes here. So same here also you can have multiple modes. So typically we call this is a 0 means actually this is a gamma point. That's the, in the brilliance zone, that is the center point. So if you consider phonon dispersion, people mostly consider this the gamma point phonons, because if you consider in both sides, right? So we have like this. So they, if you take any point here, they cancel out each other. Like if you take here, they cancel out. So you get only the gamma point. But unless you have some nanostructured material, if you have a nanostructured material, there's something called phonon confinement. That means, suppose if you have a nanowire or something, so then this doesn't go all the way, right? So you can have, depending on this, the diameter of the nanowire, you might get some contribution from this, not the zone center, from some other K values. So these are details of it. Right now, just remember, mostly people consider phonons at the zone center, that is the gamma point. So that is, and if you look at anything, people usually show going from, say, gamma point to X point. The X point is at the brilliant zone. Okay, so that's what they look like. So now if you want to calculate, so now in the Ka goes to 0, in this one, if you consider Ka goes to 0, this becomes 1, right? So then what happens? Just try to understand U and V. So how do we calculate U and V? So if you write this one, 2c minus m1 omega squared, in the limit Ka goes to 0, this becomes e to the power 0 is 1, right? That means 1 plus 1, that you get minus 2c, right? Here also you get minus 2c, then here you get 2c minus m omega squared uv. These are the amplitude equals 0, right? 0 means this one. Now you can solve this one. So this 0, if I multiply this, then how do you calculate this element? This one, 2c minus m1 omega squared times u minus 2c times v, right? This should be 0. Now if I take the u over v ratio, what do you get? U over v equals 2c over 2c minus m1 omega squared, right? So now in this case, when Ka goes to 0, you can see omega squared for minus m1 squared, so that's that. Yeah, if you do this one, m1 squared becomes, so if you plug in this one, actually you can find this one in that limit here. You will find basically this is minus m2 over m1. You have to find this relationship when m1, we calculate this once you remember m1 omega squared, okay, actually from the previous one, if you remember, m1 omega squared equals, what's that, oh here, right? Equals, oh yeah, if you substitute here, yeah, that's what I want to show. So in this case, what do you get? So omega squared, if you plug in this one, m1, if you substitute that one, you can easily show this is negative m2 over m1. Please plug in and see that value. So this means what? U and V are negative means what? That's the important thing. U is the displacement of the particle m1, V is the displacement of particle m2. So they are negative means what? One goes one way, other goes other way. So that means if your one particle goes up, other particle goes down. That's what U over V negative means. If U over V positive, that means they both go up or they both go down. So this is the important thing a lot of people miss. Acoustic modes means particle go in the same way. We call in phase. If one goes up, other one also goes up. That's the acoustic mode. Acoustic modes mean your U over V is negative number, right? Is negative. No, sorry, acoustic positive, yeah. They both go in the same direction. U over V positive means, so when one goes up, other one also goes up. This is, we call acoustic. If U over V negative, that means one goes up, other goes down. This is, we call optical mode. Why is this optical? So typically, if you take photons, right, they have this electric and magnetic fields, right? So they are basically transferred to the direction of the propagation, right? So there's some relationship why we call this optical. So, but basically, you just remember the situation. Let's look at, yeah, so this is, this happens for the negative means they are optical, not acoustic, right? So negative means these are optical. So then also I will explain what are these transverse and longitudinal. So everybody is familiar with acoustic and optical now. Acoustic means both particles in phase. Optical means both particles are out of phase. Now next thing we have to understand longitudinal versus transverse. Longitudinal means propagation direction, the particle can move, right? So even that, if you have particles like this, suppose wave is propagating this way, particles also move this way, but that can be like this. Suppose this is your U and this is V. If they are both are moving same direction, that means they are acoustic, right? That means this is longitudinal acoustic, right? If one moves this way and other moves this way, then that's a no. Still, this is yeah, optical, longitudinal. Yeah. So, but if the wave is moving this way and particles are moving, say, both same way, that means these are transverse, but this is acoustic. Suppose moving this way, both one going up, that means still transverse optical mode. That's the increment. So that's why if you see any phonons, you will see things like this. You will see transverse acoustic, transverse optic, longitudinal acoustic, longitudinal optics. You get the idea? So let me show you some of these. Please try to. So from here you say that, right? If you find U over V, from that you can tell. So let's see whether you understand this one. Let's look at. So what is this mode? So this is moving this way. Particles are moving up and down. That means it's transverse, right? So one goes up, other goes down. That means this is optical. This is optical transverse TO mode, right? So here are some of the things you can see here. Transverse acoustics means your U and V should be positive, right? Just the, yes. So let's look at. So here, what is this mode? Again, transverse, but both moves same direction. That means that is transverse but acoustic, right? Because they are in the same direction in phase. Okay, let's see. What is this one? They are going opposite direction, that means optic, right? But in the longitudinal. So longitudinal, optic mode. Optic means because they are both opposite direction, right? So what is this one? Transverse, definitely. When one goes up, other one goes down, that is definitely optical. Optical transverse mode. So what is this one? Longitudinal, acoustic, right? In the same direction. So, you get the idea, right? So everybody should have a good idea when you will always see these notations, LA, LO, TA, TO. Everybody should know what that means. And also we know. So this is still the longitudinal acoustic, but you compare to previous one, this has higher frequency, right? So here's, what is this one? We already talked about that, right? So this again, this acoustic, right, in the same direction, but transverse. So here's one acoustic and optic mode. You can see this is longitudinal, right? So if you consider this is optical, typically optical modes have much higher energies, because we know that one energy is basically omega, right? Here, even at the zone center, so these have much higher frequencies if you can. So optical modes always have higher frequencies. Okay, so everybody can
we always consider the neighboring atom for.
Yeah, so everything is, yeah, even if you consider next nearest neighbors, still the qualitative picture is the same. But that expression is very complicated, right? That's the problem. Okay, so actually these phonon modes, people have really observed. So for example, if I, oh no, this is before that, so this the basic summary, right? Acoustic, optical, then there are some energies, there are no allowed modes, right? So we call this a photonic band gap, because that's very important. There are something called photonic crystals, so I don't know whether you have seen. So if you take these opal structures, so you can make it like FCC structure. You will, if you look like this, you will see nice colors depending on the direction. These are, because of that, we have certain this band gap. Everybody, that's what we are going to discuss next time. The band gap for electron states, right? But these are band gap for the phonon states. So there are no phonons available in this energy range. Here, at any of this energy, you have some acoustic phonons, right? Any of here, you have phonons with optical, but there are no allowed phononic state for that particular energy. That's a quantum mechanical picture, right? There are only certain ranges. So this is the important thing. In this general expression, if you have a 3D material, so for p atoms per basis, so in the first case, how many atoms we considered? Previously 1, right? So typically we have 3 acoustic modes. So that's true, right? Remember, we even experimentally we showed this one. Actually, looking at 1, 0, 0 and 1, 1, 0, we saw like 3 and 2. Typically you have 3 acoustic modes. So in this case, did we see any optical mode? No, right? But if we have more than 1 atom in the basis, typically we are talking about p minus 1 number of group of optical modes. Group means still you can have this transverse and longitudinal. So if you have 1, that means you have 0 optical modes, right? But if you have 2 atoms, that's what we consider, right? Then you have 1 optical mode, right? So that's what we had this one. If you have 3 atom bases, then you can have 2 optical modes like this one. This is some general expression, but you can see some, in many cases, some of the these modes can be degenerate. You can only see longitudinal 1 and 1, this transverse. This is a very general statement. Okay, so here people have studied how light interact with some phonons. Actually, like I said, optical phonons have much higher energies, right? So actually, typically they are in the range of 10 to the power 13 hertz kind of frequencies. So now if I have some, say, IR radiation, H nu, so if I have some material, right, this already has some phonons, right? Suppose this is some optical phonon in this energy range, say 10 to the power 13 hertz. So then what happens? That photon will interact with this photon, so then the outcoming energy will have reduced energy, right? So now if you look at your absorption, the transmission or reflectance, actually they have measured the transmittance. That means, so this is transmittance is pretty constant. Here transmittance is going down, means it has high absorption, right? So that means it absorbs because of what? To excite that optical phonon. So if you look at this one, comes exactly at frequency around, you know, this is in wavelengths. So you know how to convert wavelength into the energy, right? If I told you about EV equals 1.23 divided by your lambda in micrometers, right? Like that you can calculate everything. So if you know, basically, if you know the phonon frequency, so you can calculate your wavelength and everything, right? Frequency. This is wavelength. So this, what is this absorption? That is the absorption due to that optical phonon. This is actually the experimental results for sodium chloride film. This is simply, if you do this one for lithium chloride, what do you expect? Lithium has lower mass, right, compared to sodium. That means your frequency should, so frequency goes like square root of 2c over m, right? So that means your smaller mass means higher frequency, that means larger wavelength. So actually if you do for lithium chloride, you will see that lower wavelength, that means higher frequencies. Is that clear? So depending on, because frequency goes like 2c over m. Okay, so now let's go back, and I want to remind you, we talk about the phonons, right? Phonons means when the atoms are vibrating, so we find that disturbance moving as a wave, right? That's basically phonon. So we showed this average number of phonons. This is a very important thing to remember. We showed this one using Maxwell-Boltzmann distribution, right? Please remember this expression, this is very important. The average number of phonons, this number of phonons is given by 1 over E H cross omega over KBT minus 1. So that means number of this harmonic oscillators, right? So that's basically average number of, so for a given temperature, this is the average number of phonons, so average number of those simple harmonic oscillators. So then the average energy, if you remember, average energy basically multiplied by H cross omega. So this is, these two everybody should remember. Cross omega over KBT this is the average energy, this is the average number of phonons. You can see when your temperature is very small, average number of phonons will be low, right? Because your vibrations becomes limited. So these two are very important. If you want to put the 0 point motion, you can write this way. But typically, we write h cross omega over this one. This is the average energy, including the 0 point energy. So then if you represent this oscillator as a wave, we write this one as some phonon wave, right? So this E, I, K, X, that's what we did. These three things, please remember, this is very important. So remember how we derive this equation, right? It's basically take one state, then divide by the probability, right? So okay, so now we'll talk about this very last thing, phonons and conservation laws. So we talk about these phonons as these waves. So that means it has the frequency omega, that's the frequency of this simple harmonic oscillator, right? If you take this energy, this is h cross omega. So then it has this quantized energy states, right? That's what the harmonic oscillator is. Now, since this is a wave, we know waves always carry energy, right? So also, any wave can carry energy and momentum. But the particles, they don't move, right? So if you take any wave, right, even the simple mechanical wave, so what you have, if you have a string, right, if you have like this, so these particles just move up and down, then your energy is transferred along the wave, right? Energy as well as momentum. But the mass just doesn't move, right? There's no mass transfer. So for this reason, when we call about this the momentum, so this is not a linear momentum. If you have a linear momentum means P equals mv, right? So that means your mass is moving. So here we don't have any real mass transfer. For that reason, for these phonons, we call it not the linear momentum, we call it as a crystal momentum. This is an important thing to remember. Definition of a crystal momentum given by, so we know momentum is given by h cross omega, right? So h cross k. Energy is given as, everybody remember this one, right? Energy is given as h cross omega. Momentum, typically h over lambda, right? So this is, h means h cross is h over 2 pi. If I write h as 2 pi times h cross, k is defined as 2 pi over lambda, right? So that means 1 over lambda means k over 2 pi. So then if you the 2 pi cancel, you get P as h cross, you know how to write this. So typically the energy is h cross omega, momentum is given by h cross k. But this h cross k is not a linear momentum, please remember. This we call is a crystal momentum. That's because there are no real mass transfer. Okay, these are. Okay, now let's talk about conservation laws. So, at a given temperature, you can have more than one phonon, right? Because in the phonon spectrum, you can have several phonons corresponding to these energies, right? Or wave vectors. That means at a given time, you can have several phonons. That means you can have like one wave like this, another wave like this, and another wave like this, right? So there are several phonons. So these phonons can interact with each other. They can collide with each other, So if that happens, these phonons should still obey the conservation of momentum and conservation of energy. So if I have two phonons, suppose that has omega 1, omega 2, if they add, suppose you have third phonon omega 3, then you have to follow the momentum. So first energy conservation, you have H cross omega 1, here you have, this is before. This is two phonons colliding, right? So making third one, so H cross omega 2 equals H cross omega 3, that's energy conservation. But how about momentum conservation? So that depending on what is the energy of the phonons. So if you have this one has wave vector k1, this is k2, then you can have H cross k1 plus H cross k2. This should be, this one has a k3. So this is H cross k3 if it is very low energy situation. If it is high energy situation, you need to have this reciprocal wave vector to conserve that. So I will explain later why we need that one. Probably you remember this one, right? If you have photons, if I have say X-rays, K1, K2, what is K2 minus K1? Bragg's law, delta K is G, right? So that means you have H cross K, if I take K2 equals H cross K1 plus G, right? Is something related to that one. So this is a difference in your K vector is really, that's the Bragg's law, right? Delta K equals G is somewhat similar to that one, but this is for photons. But here we are talking about what? What are these? These are phonons, right? Yeah. But remember, they both are quasi-particles, right? So they have some quantized this, energies. So please remember this one, say omega 1, omega 2, making the third phonon omega 3, but in terms of the wave vector, but you can have this one without this one, but I will explain this one. This is called the normal process, so this is called some process. So here, this is what I'm trying to explain for the photons. So just a special cause of general conservation. Now, this is the more general situation, but this is also true if it is smaller energy. So I will show you that one in the next couple of slides. Okay, so now, so we need to get back to our brilliant zone. So everybody remember this one. So this is my first brilliant zone, right? Second brilliant zone, third brilliant zone, and so on, right? So, like I said, you don't need to do anything other than first brilliant zone. If it is somewhere here, you only have to do is subtract G vector. What is G vector here? This is pi over A, right? So 2 pi over A. So if you subtract that one, actually 2 pi over A. G is 2 pi over A, right? For the simple cubic. That means if you subtract G, if this is 1, if you subtract G, what happens? This point becomes this point, right? If it is here, that point becomes this point, right? So any point away from the first brilliant zone, I can bring it back to first one by subtracting G vector. That's the whole idea. You don't have to worry about anything other than the first, here, second brilliant zone, third brilliant zone, So now everybody remember how we did the weakness side sets, right? So basically take the closest one, and so, but if you do this one in the reciprocal space, what did you get? That's the brilliant zone, right? Brilliant zone means your weakness side cell in the reciprocal space. So here. So this is what I was trying to say. If you have any point here, you can basically bring it back to this point by subtracting your g vector. G is 2 pi over a, right? If you remember, g, we write that 2 pi over a, your x. Yeah, x plus y plus c, right? So if it is a simple cubic, that's basically same in all the directions, right? So this is one-dimensional case we are showing. You can see just by subtracting by g, you can bring it back to original. So this k1 means k minus g, right? That's basically. So that's what we are trying to say. You don't have to worry about anything other than your first region. So that's the g vector. Is that clear for everyone? Yeah. Like I said, this brilliant zone for other three-dimensional case is pretty complicated, right? So this is the one gamma point. That's what we are talking about. K equals 0. This point k equals 0. That's the point we have gamma point, right? If you go from gamma, this is the border of your brilliant zone, right? That's what you are getting here by your a. This is basically x point. So you can go from gamma point to x point to different points. L means center of this one. So these are some symmetric points. Don't worry about that. If you see somewhere gamma point, everybody should know. That's the zone center point. That is k equals 0 point. Typically, x point is basically a brilliant zone. Okay, now next very important two things I want to talk about. So far we talked about simple harmonic oscillator, right? So that means we have very symmetric simple harmonic oscillator. If you write the energy, this is half k x squared, right? So this is, we call the harmonic. Harmonic means these are very symmetrical from both ends, right? But there are two things you cannot explain assuming perfect harmonic oscillator. One is the thermal expansion, other one is the thermal conductivity. Because if you take your thermal expansion, what is thermal expansion means? If you look at the average displacement, if it is expanding, that average value should have finite value, right? But if you calculate your average x, so how do you calculate average value typically? Boltzmann. So if you want to find x, what is the average x? You multiply by E minus is u over kBt, right? So then divide by your energy kBt. That's how you calculate the average value of x, right? So any function, if you want fx, you just fx multiplied by this Boltzmann factor divided by the Boltzmann integral here. But in this case, what is your energy? U is the times this dx, right? Your ux is half k squared. So if you plug in this one, you can easily calculate this x value, this x times kBt. So ux, just plug in half k squared. So if you do that one, what do you get? So this is cx squared, this is cx squared. If you calculate this one, this number is 0. Do that integral. So what does that mean? That means your average value, there's no expansion, right? So that's because we assume this your function to be perfect, the symmetric oscillator. So this is, if you calculate this one, the value is 0. Also doesn't depend on your temperature. We know that's not true, right? Everybody knows if you heat a material, typically its length is changing as L0, 1 plus alpha times delta t, right? So it has a linear t dependence, right? So typically your x average goes something like t, but this one gives you 0. The problem is our assumption of u is wrong. For that reason, we have to introduce for these two situations anharmonic oscillator. So that means your oscillator is not like this. Instead, it should have some anharmonicity, like maybe doing something like that. One side is we call it anharmonicity, right? Because there's no harmonicity here. So if you do that one, you can get this expression. For that, we are going to introduce new function. Yeah, so we replace ux by this expression, not just x squared. Just put some x squared and x4 terms. So then your oscillator will be, this is the how your so this is the perfect simple harmonic oscillator. If you introduce second and third order, it becomes something like this. That is not harmonic, right? Now it has an harmonicity. Now you can go ahead and calculate your average value. Then what happens here? U becomes basically now ax squared plus bx u something x4 something like that, right? If you do this integral, I will give this one as a homework problem. You can easily do a simple integral, right? If you do that one, you get your x bar goes like t. So that explains your the t dependence. Actually, experimental people have measured for this argon crystal at low temperature. So argon at low temperature, they form some FCC crystal. So if you look at this one, you can see this lattice constant. They measure the lattice constant. Lattice constant is basically expansion, right? If it changes with temperature, that tells you this. So if you measure that one, actually you find here this part is pretty linear temperature dependent. This is a real experimental data. And also density. Because if the expansion changes means your density is also changing, right? So next thing is, yeah, so x goes like t. That you can, if you introduce this, not just the quadratic, right? If you have higher order thing, you get the t thing. You will do this one for the homework problem. That we know from this one. Okay, so the next thing is thermal resistivity. That one also you cannot explain using this simple harmonic oscillator. That's because why do we have this phonons? So these phonons, if you have phonon moving without any, suppose this is infinite material, there are no boundaries, right? These are going to infinity from every direction. So these phonons, they can just keep moving, right? So that means they can carry your heat, right? So these are the phonons. If you provide some heat, so that heat is carried by these phonons to the other end, right? So that means if there are no any resistance for this flow, then you will have infinite conductivity, right? So that's what this says, right? When thermal energy propagates through a solid, so they are carried by lattice waves, right? So that's what the phonons are. If the atomic potential energy function is harmonic, lattice wave obeys the superposition. So harmonic means, so you have these waves coming from these different phonons, right? So they can superimpose. When you superimpose, what happens? The effect becomes more stronger, right? That's what superposition means. That means they can move, suppose there's one phonon carrying this one, there's another phonon carrying this one. If they both superimpose, so then they can carry more, right? So then if we superimpose with another one, that can carry even more heat. So that means that heat conduction becomes infinitely easier, right? So that happens if you consider this all harmonic oscillator assumption. But if you have anharmonicity, then these waves don't easily, everybody remember the superposition, right? To have superposition, you need to have same frequencies and same, it should be in phase, right? If you have anharmonicity, then they cannot superimpose because it violates some of the conditions. That means this conduction doesn't happen indefinitely. If it is a harmonic, that means they keep accumulating the heat conduction, so that will give you infinite, we call it the heat conductivity becomes infinite. So, but if you can introduce harmonic oscillators, that means these, they don't really, the superposition is not going to happen. So that means you have some kind of even, we know this thing, they can even make constructive interference kind of thing, right? So then your conduction mechanism becomes low. That means you have a finite conductivity. This is a simple harmonic oscillator to give you infinite conductivity. But if you assume as asymmetric anharmonicity, right? Anharmonicity will give you a finite conductivity. That's the whole idea. So now if you look at, we can calculate the thermal conductivity. I think this is important. No, everybody familiar with this equation? This is something everybody should remember, how the heat capacity is related to the thermal conductivity. The 1/3, this is only true for the 3-dimensional case. 1/3 of your heat capacity that we already showed, right? What was the CV? Anybody remember? Heat capacity for low temperature was going like T cube, right? So this is only phonons, right? So at high temperature, what was CV? 3R, right? So this CV is related to K by this number 1/3 of that CV that we have here times your velocity of your phonon times the, we call the mean free path. What is mean free path means? It's phonons, right? So if you have phonons, so if they can move without any problem, so then your mean free path is infinite, right? But there are places these phonons can get scattered. This is a very important phenomenon. That's how people try to tailor the thermal properties of materials. If somebody wants to reduce your thermal conductivity, what you have to do is introduce more phonon scatterers. if phonon is moving like this, if they can get scattered, your heat, the thermal conductivity becomes less, right? Where can they get scattered? Can you imagine? This is a material, right? If it's a finite material, they can always get scattered from the boundaries, right? If the phonons are moving this way, they can get scattered from the boundaries of the sample. Or if you have, say, a polycrystalline sample, what are these? Grain boundaries, right? So these phonons can get scattered from the grain boundaries. So grain boundaries are very important places they can get scattered. Or if you have some phonon, it can get scattered from another phonon. Remember we talk about two phonons colliding, right? So they can get scattered from other phonons. They call the phonon-phonon interaction. So that makes your gamma finite, right? If you, what is the mean free path means? The maximum distance they can go without getting scattered. If you have no scatterers, gamma can be very large, right? If you have too many scatterers, gamma will be small. So if you want to make your, I don't know whether anybody working on thermoelectric materials, there's something called this figure of merit that is given as this Seebeck coefficient. This is C, yeah. S squared sigma over kappa. So that means if you want to get higher figure of merit, this is the Seebeck coefficient, this is the electrical conductivity, this is the thermal conductivity. We are going to, next chapter we are going to talk about the electrical conductivity. So far we have been talking about thermal conductivity. If you want to get higher figure of merit, you need to have very small thermal conductivity. But you cannot, still you need to maintain higher electrical conductivity. So this is very tricky problem. So there are a lot of ways people try to address that one. So your electrons can pass through some areas, but phonons can get scattered. That means sigma is still not affected, K can be reduced. So that's very important thing. Yeah.
What's the left hand side?
What's that?
What's the left hand side?
Oh, this is it's called the figure of merit, C factor. That's how good your material is. So this is the important thing. Later I will talk about this one. We need to reduce K. Reduce K means you have to introduce more and more phonon scattering. Okay, so how do you derive this equation? It's very simple. Everybody remember this equation? This is the heat flux. This means heat per unit area per unit time, right? J is given as minus K times. This is the temperature gradient. If you have T, the difference delta T at a distant Tx. Everybody remember this one, right? So J means actually, J means per unit area. This is a heat per time, right? Heat per unit time. That's what this one. So if you actually write this, let me quickly show the derivation. So this is, everybody can understand this one. J means 1 over A dq over dt, right? So now I can write Q as, for a unit mass, thermal, what is the heat, specific heat capacity, right? Heat capacity times temperature difference divided by A. So T, if I consider this time for a collision between two phonons, so phonon with another thing, I can write this one as tau. So now if I write tau as V divided by gamma, because this is, you have, this is my gamma between two scattering centers, right? So if it is moving at velocity v, then I can write the time between these two scattering events, that's given by your gamma over v, right? Basically distance over velocity. That's what I put it here. C, this is fine, right? Q means C times dt, temperature difference. So divided by A. If I consider that time as tau, then I write tau as gamma over V, right? So now you can see, now this is volume, right? A times gamma means volume. So that means if you divide C by this one, we call the heat capacity per volume. So that's CV, delta TV. Now, if I write this one, delta TV, delta T I can write as delta T divided by delta X times gamma. Right? So that's same thing. So if you do this one, you will get CVV gamma, then you have delta T over delta X. Right? So now if you compare these two equations, what is this? You have same J equals, so this K means this one, right? So your K is basically the heat capacity is CV times the V times gamma. But this is in one direction. But you have heat propagated in three directions. That means really you get 1/3 of that one, right? So that's how you get this expression, 1/3 CV times V times gamma. Also you can write gamma means really V times tau, so you can write any way you want. But everybody should remember this one, this is important. So how to relate thermal conductivity to the heat capacity. Okay, so we talked about this phonon scattering here. These are the basic mechanism to consider in phonons. Impurity or grain boundaries in polycrystalline sample boundaries, these are the scatterers, right? Even impurities, if you, in this one, if you have some kind of impurity, this phonon can get scattered from those impurities. Yeah?
Is that the same as like a defect? Is that the same as defects?
Defects, yeah. Impurity can be defects, yes, yeah. Even point defects or even line defects. So even some heteroatom.
Is that a consequence of the grain boundaries?
Grain boundary is basically the border between two different crystallites, right? Yeah. That's the whole surface there. Then other phonons. So that's because we have this anharmonicity, right? Now let's see how the thermal conductivity changes with temperature. So if you do this one, let's do this one very carefully. So now we know kappa is going as 1/3 your CV times V times gamma, right? So now we know with temperature how CV changes, right? Low temperature TQ, high temperature 3R. Velocity doesn't change too much with temperature. You can forget about this one. Only thing you need to know is how CV and gamma changes with temperature. How is gamma changing? Just imagine phonon scattering. You have some phonon coming here, right? If you have a lot of phonons here, so they can get scattered from these phonons, right? That means if you have more phonons, that means your gamma is going to be smaller, right? So remember, what is the phonon average number of phonons? Average number of phonons, if you remember, 1 over kBT minus 1, right? So that means gamma depends on what? Gamma is inversely proportional to n, right? Because if you have more phonons, your gamma will be smaller because you have more scattering, right? That means I can say gamma is 1 over n, that means this goes upstairs, right? You have E h cross omega over kBT minus 1. That's all you need to know. Now let's look at low temperature. Low temperature. First you need to So forget about this V term, it doesn't have much temperature dependence. CV, how does it change? As T cube, right? So how about here? Here, gamma becomes what? T small means this whole thing is very large. That means this becomes infinite. So that means your gamma becomes low T, your CV, this is CV, goes like this one. Gamma goes like what? It goes to infinity. But is that real? It never goes to infinity because it always gets scattered from the surface boundary. That means this becomes some finite value, right? Ideally, it is infinite, but we know phonons never goes to infinity. They get scattered from finite sample boundary. That means this becomes finite. Then what is the total? The kappa becomes T cube times infinite means it goes like T cube, right? Is that it? Okay, now high temperature, what happens? High temperature, CV goes like 3R. Gamma goes like, high temperature means this term becomes small, right? That means Ex you can write as x plus 1, right? So that means Ex minus 1 means x. That means this goes like h cross omega over kBt, right? So that's, is that clear? H cross omega over kBt. That means if you, yeah, that's correct, right? So that means if you calculate take the product, because kappa is 1/3 CV V times gamma, right? So CV times gamma, that means if you multiply these things, this goes like 1/T, right? So kappa goes like T cube for low temperature, 1/T as high temperature. So that's actually here. Here all the details are here. Yeah, please go through this one. So everything I discuss here. So gamma really infinite, but really it's not infinite, it becomes finite, right? Here it is. Actually, this is true. If you look at thermal conductivity, temperature dependence, this is how it looks like. You can see higher temperature, they go like 1/T, but lower temperature, it shows T cube. Yeah, so then it's almost right. Okay. Okay. So I need maybe 5 minutes from next class then. So I will discuss that in next class. So then we'll start the electronic properties. I think that's what for most of people in the semiconductors and things like that. Okay. So this week no homework, right? I will give you homework this Thursday. How was that? So, stat mac exam? Not bad?
It was
Better than
It was better.
we expected.
Oh, really? Okay.
we were expecting lots
Much worse?
much worse.
Oh.
But it was long, like we started around.
We started at 2, we ended at 7. Well,
Yeah, this
I
is
was-
Dr. Wu's methods. So he used to give pizza